It's not the right form yet. So we got to somehow get into this form. And this goes back to Caleb's comment once. The course should have a 2-hour tutorial on indicator functions. I think you said that once. Yeah, halfway through the course. Because, basically we have a yi there. And the result says that no, we have to have a summation of ci log pi. And so we have that problem. So to deal with that, we need another summation and an indicator function there. And then we see what CL is that without the sum there. So what is it? Somebody tell me. So I've got my CL. Is hidden in there. And again, I have to take that sum outside. In this lemma, it's a sum I equals 1 to t. And then ignore the sum over L, and I get a gamma Ri upside down. Times an indicator function that yi equals L. And let's see if that looks intuitive now. All right, so we get our bk plus 1 from R to L, if you like, is the maximizer from this lemma. So it's this over its sum. So it's not quite the same kind of average. So it's this. I'll write it down. I equals 1 to t. But again, the way something was killed off before, it gets killed off here now too. So the summation over L, the indicator function y equals L, there is no not a number. You see something. So that whole thing is 1. Just as before. So, so there you have it. You have this strange sort of, here we have the probability that we see an I and an indicator function at y equals L. I think it would take you longer to come out of the cave and come up with that answer. This one is way more intuitive than that. I don't know. Does somebody disagree? No? Well, I saw something. You know what I mean? So yi is something. And I'm summing all possible things it could be. So it's 1. Yeah. And so that's that. So there it is. You can imagine how quick it is to code, except for, again, these monsters.
So you're saying the bottom inner sum never not be nothing?
No, yi is something. So I said that the observations take on values, the integers 1 through m. And so if I I'm summing the, is it 1, is it 2, is it 3, is it 4? And I get up to m, is it m? And if you said no to all that, then my mod's not valid. I said the model, the observations take on values 1 through, say, 25, And so, yeah. Oh, yeah, well, take a look at this. I'm trying to apply this lemma. And there's no transformation of either, Yeah, I've got to do something to get in this form. And the only way I know how to do it is to make use of my favorite trick is for an indicator function. So, yeah, and you have to have it because your answer does have an indicator function. If you look at, you count up the number, for each L, you count up the number of times the y equals L, and you look at the probability that Z happened, and you average those out. Yeah. So you're going to need a lot of data to fit this for a big model. It's going to be really slow.
Did you brush anything under the rug?
No. I mean, I've got this elegant little. The only thing I did is we went really slowly and proved this tiny little result, and then we see it appears everywhere. In each of these cases, maximizing this for each R, maximizing that for each R, subject to these constraints, it exactly fits in that lemma. So in each case, we have to identify what is P and what is C. And then we go through and we normalize. We look at C over P. We take C over its sum, and that gives us the optimizer. Nothing under the rug. No, what's bothering you? Come on. I mean, I'm just applying this lemma.
I think there's something hidden.
Nah. Well, I think the separability could bother you. I mean, that bothered you. But just look at this. For each R, I've got a coupling. For each R, I've got a coupling to this sum, and a coupling to this sum. So I have to solve an optimization problem for each R here and for each R here. But once you do that lemma just nails it. You're done. This beautiful lemma. It's just a notation so ugly. That's all. Here you've got a pretty little CI, and then you've got CI is a horrible mess. That's all. Yeah. All right. And it'll be clear when you code it. So so we are going to broadcast the homework assignment soon, and I want you to code this just to see how simple it is. Feel free to find an M file for these guys, for these conditional probabilities. If you can't find, well, someone here will have it, broadcast it to everybody else. But it'll just be a few lines of code, and it'll take some time to run. You can imagine. You need a lot of data to make this reliable, so we'll send you a lot of data. We've got a helicopter. I'll tell you the truth. You see, Dora's off at Lake Alice, and she's going around in circles right now, and the helicopter, just didn't come. We'd booked it for last week, and it didn't show up. And if you go down to Lake Alice today, you'll see a helicopter collecting data, and it'll be ready by tonight. And we have to go and clean it up for you, and then you'll be ready to go. All right. So that's it. I mean, I don't think any of us have the energy to look at Gaussian processes or large deviations from Markov chains or, I don't know, anything else. So, I mean, I'll give maybe a overview of what I think is important in the course on Tuesday, and then I'll just stop for office hours, okay? But please show up, because it'll be good to have a discussion, all right? And fill out those evaluation forms, and I'd love to get feedback in the course later on. So after the grades are done and all that, I'd love to get feedback, and just let me know. All right, but that's it for now.